welcome to a deep dive into something that, well, might seem deceptively simple at first.
Okay.
How we move through space. You might think, well, the Earth spins, right?
Yeah.
But it's a lot more intricate and fascinating than that.
Right.
Today, we'll be drawing insights from this incredible Vsauce video titled Metin Yapıştırıldı.
Okay.
It's full of surprising science and quirky facts that really make you think.
Yeah, it really does a fantastic job of showing how deeply intertwined our lives are with Earth's movements. I mean, everything from calendars to time zones, even some historical quirks, all can be traced back to this cosmic dance we're all a part of.
I'm already intrigued. So
Yeah.
let's kick things off by shattering that simple image of Earth just spinning on its axis.
Exactly. Imagine Earth as this massive, wet rock spaceship,
Yep.
as Vsauce puts it, hurtling through the vastness of space.
Mhm.
Not only are we rotating on our axis,
Right.
but we're also revolving around the sun, all while tilted at a 23.4-degree angle.
That tilt always fascinated me. I know it's the reason we experience different seasons,
Right.
but could you unpack that a bit more?
Absolutely. Think about it this way. Because of that tilt, different parts of the Earth receive, varying amounts of direct sunlight
Mm-hmm.
throughout the year. So when your hemisphere is tilted towards the sun, you experience summer, longer days, warmer temperatures.
Yeah,
And then when it's tilted away, winter sets in.
that makes sense. But speaking of time,
Yeah,
this is where things start to get really interesting, wouldn't you say?
it does.
We're so used to our neat 24-hour days that
Yeah.
our source material
Yeah,
dives into some fascinating nuances about how we measure time.
it does. And it all boils down to the difference between a solar day and a sidereal day. So a sidereal day is the time it takes for the Earth to complete one full rotation
Okay.
relative to the distant stars. And it turns out a sidereal day is actually about 23.9 hours long.
Wait, so a day isn't actually 24 hours long.
Whoa!
What's going on there?
The 24-hour day we're all familiar with is based on the solar day,
Okay.
the time it takes for the sun to appear in the same position in the sky. But because of Earth's elliptical orbit and tilt, this solar day isn't always precisely 24 hours. Sometimes it's slightly longer, sometimes slightly shorter.
So our clocks are technically lying to us?
Not intentionally. They're
Yeah.
just trying to keep up with the celestial system that's inherently a bit messy.
Yeah.
This discrepancy between our neat 24-hour clock time
Right.
and the actual solar time
Yeah.
is where the concept of the equation of time comes in.
The equation of time. This is one of the things in the video that really made me pause and think.
Yeah.
What are the real-world implications of this equation? Was this just a scientific curiosity, or did it actually affect people's lives?
It had a huge impact, especially before the invention of accurate clocks.
Wow.
You have to imagine a time when people relied on sundials to tell time.
Oh, yeah.
Because of the equation of time, a sundial wouldn't show the same time as a mechanical clock. In essence, people had to constantly adjust their timekeeping
Wow.
throughout the year.
I never thought about it that way.
Yeah.
Now, there was another concept in this video that completely blew my mind.
Okay.
The subsolar point. Imagine, at any given moment, there's one specific spot on Earth
Right.
where the sun is directly overhead.
Yep.
That's the subsolar point.
And here's where it gets even more fascinating.
Okay.
This point isn't static.
Right.
It's constantly moving, tracing a figure-8 path across the globe throughout the year.
So let me get this straight.
Yeah.
That means at some point during the year, the subsolar point could be directly over my head.
It certainly is. However, the subsolar point only passes directly over land in a few specific places. One of those places is Hawaii, where you can witness a phenomenon called Lahaina Noon.
Lahaina Noon. Tell me more.
Picture this. You're in Hawaii,
Okay.
and the subsolar point passes directly overhead. Shadows practically vanish. As the sun aligns perfectly with the zenith, objects appear to have no shadows at all. It's like stepping into a surreal, shadowless world for a brief moment.
It sounds like something straight out of science fiction. Okay, so we've got this wet rock spaceship spinning, tilting, revolving
Right.
with the subsolar point tracing this crazy figure-8 path.
Yeah.
It makes you wonder how anyone ever managed to create a calendar that makes sense of all this cosmic chaos.
It was quite a challenge, to be sure, but that's precisely why we have leap years, isn't it?
Right. Leap years always seemed a bit arbitrary to me.
Yeah.
But they're actually a clever way to ensure our calendars stay in sync with Earth's journey around the sun.
Exactly. You see, a solar year, the time it takes for the Earth to complete one full orbit around the sun, isn't exactly 365 days.
Yep.
It's actually about 365 and a quarter days long.
Oh, wow.
Those leap years, with their extra day, are essential for keeping our calendar in alignment with the actual solar year.
So they're like a cosmic course correction. Speaking of calendars, didn't different civilizations have different ways of tackling this calendar conundrum?
Absolutely. Throughout history, there have been numerous attempts to create calendars that accurately reflect Earth's movement. For centuries, the Julian calendar was the standard.
Right.
But it had a slight flaw. It overestimated the length of a year by just a tiny bit. But over time, that tiny discrepancy added up.
And that's where our current calendar, the Gregorian calendar, comes in, right?
That's it.
It swoops in to save the day.
Precisely. In the 16th century, Pope Gregory III decided they did, at least in countries that adopted the Gregorian calendar right away. Imagine the chaos that must have ensued. It's one of the reasons there are 2 different recorded birthdays for George Washington.
Wow. Who knew George Washington's birthday had such a cosmic connection?
Mm.
So it's incredible to think that something as seemingly mundane as our calendars is intricately linked to the complexities of Earth's movement.
It really highlights how much our everyday lives are intertwined with these grand cosmic movements, even if we don't always realize it.
Well, my mind is officially blown. But we're just getting started on our cosmic journey, aren't we? It's time to zoom out and explore the mind-boggling speeds at which we're hurtling through space.
That's right. Fasten your seatbelts. Things are about to get really wild as we venture beyond our planet.
So far, we've been focused on Earth's individual movements, spinning, the tilting, the revolving. But the Vsauce video, it takes us on an even wilder ride when we zoom out and consider our place within the solar system and the galaxy.
That's where the true scale of our cosmic journey becomes apparent.
Right.
It's not just about Earth's movements. It's about our solar system's movement within the Milky Way galaxy.
Yeah.
And then the Milky Way's movement through the vast expanse of the universe.
It's mind-boggling to think about. I have to ask, how fast are we actually moving through space? Like when we consider all these layers of motion.
Prepare yourself, because the numbers are truly astonishing. So let's start with Earth's orbit around the sun. We're zipping along at a speed of roughly 108,000 kilometers per hour.
108,000 kilometers per hour. That's already incredibly fast.
Yeah.
But I have a feeling that's just the tip of the iceberg.
You're absolutely right.
Okay.
Now imagine our entire solar system, the sun, all the planets, including Earth, hurtling through the Milky Way galaxy at an average speed of 792,000 kilometers per hour.
Wow. That's more than 7 times faster than Earth's orbital speed. It's like we're on this grand cosmic racetrack, constantly in motion.
Yeah.
But where are we heading at these incredible speeds?
That's a question that has puzzled astronomers and astrophysicists for decades.
Yeah.
We know that our galaxy, along with a cluster of neighboring galaxies, is being pulled towards a mysterious gravitational anomaly known as the Great Attractor.
The Great Attractor. It sounds almost ominous. What exactly is it? Do scientists have any idea?
It's a region of space with a tremendously strong gravitational pull, influencing the movement of galaxies across a vast region.
Right.
However, its precise nature remains a mystery. It's obscured by dust and gas in the plane of our Milky Way, making it difficult to observe directly.
So we're essentially on this cosmic road trip, hurtling towards an unknown destination at unimaginable speeds. It's both exhilarating and a bit unsettling.
It certainly puts our place in the universe into perspective, doesn't it?
Yeah.
But there's another fascinating element to this cosmic puzzle: the cosmic microwave background radiation, or CMB.
Cosmic microwave background. That sounds familiar, but I need a little refresher.
Right.
Could you remind me what that is?
Imagine you could look back in time, almost at the very beginning of the universe, to a point about 380,000 years after the Big Bang. The universe was incredibly hot and dense back then. As it expanded and cooled, light from that early epoch began to travel freely through space.
Okay.
That ancient light, now stretched and shifted to microwave wavelengths, is what we detect today as the cosmic microwave background.
So it's like a faint echo of the Big Bang, the earliest light in the universe reaching us after billions of years. That's incredible.
Hmm.
But how does the cosmic microwave background help us understand our movement through space?
That's where things get really interesting. The CMB isn't perfectly uniform. There are tiny variations in its temperature across the sky. By studying these variations, scientists can determine our motion relative to this ancient light.
Wait, so by analyzing these subtle temperature differences in light that's been traveling for billions of years,
Right.
we can actually figure out how fast and in what direction we're moving.
Exactly.
That seems almost like magic.
It's a testament to the ingenuity of scientists and the power of scientific observation.
Yeah.
You see, the CMB acts like a cosmic reference frame, a backdrop against which we can measure our motion.
Okay.
As we move through space, the CMB light we observe from different directions gets slightly Doppler shifted.
Doppler shifted. You're going to have to break that down for me.
Imagine an ambulance siren. As it approaches you, the sound waves are compressed, making the pitch higher. As it moves away, the sound waves stretch out, lowering the pitch.
Right.
That's the Doppler effect with sound. A similar thing happens with light. As we move towards a source of light, its wavelengths get compressed, shifting towards the blue end of the spectrum.
Okay.
As we move away, the wavelengths get stretched, shifting towards the red end.
So by observing these subtle shifts in the CMB's wavelength, scientists can tell if we're moving towards or away from certain regions of the early universe.
Exactly. And by analyzing these shifts across the entire sky, they can build up a comprehensive picture of our motion relative to the CMB. It's like using a cosmic speedometer to track our movement through the vastness of space.
I'm starting to grasp the immense scale of what we're talking about here.
Yeah.
We're spinning, revolving, hurtling through the Milky Way at incredible speeds. And all of that is moving relative to this ancient light from the Big Bang. It's truly awe-inspiring.
It is, and it shows how far our understanding of Earth's movement has come.
Yeah.
We've gone from observing the sun's movement across the sky to tracking our motion through the universe.
Right.
Using light that's been traveling for billions of years.
It's a testament to human curiosity and our desire to understand our place in the grand scheme of things.
Speaking of which, I'm curious to explore the philosophical implications of all this. How does this knowledge of our constant cosmic journey change our perspective on life, time, and our place in the universe?
That's a great question, and one I think we need some time to unpack. It seems like there's so much more to uncover, both scientifically and philosophically. It really is incredible to think about everything we've discussed, from Earth's rotations and revolutions to the solar system's journey through the galaxy and the Milky Way's movement through the universe.
Right.
It's a lot to wrap our heads around.
It is, and that's precisely what makes it so fascinating. We're not just passively sitting on a stationary planet. We're active participants in this grand cosmic dance that's been unfolding for billions of years.
It almost makes those everyday worries seem insignificant, doesn't it?
Yeah.
I mean, when you grasp the sheer scale of the universe and our place within it, it's both humbling and strangely liberating.
I completely agree. It's a powerful reminder that we're part of something much larger than ourselves, a cosmic narrative that extends far beyond our individual lives.
It brings to mind that famous Carl Sagan quote, "We are a way for the cosmos to know itself."
Exactly. We're not just observers, we're an integral part of this vast, interconnected universe. And every new discovery, every piece of knowledge we gain about our cosmic journey adds another layer to that incredible story.
It makes you wonder what other mysteries are out there waiting to be uncovered.
Right.
What will we learn about our place in the universe in the years to come? What new perspectives will future generations have?
That's the beauty of science, isn't it? It's a never-ending quest for knowledge, a constant exploration that pushes the boundaries of what we know and understand.
Yeah.
There's always something new to discover, some new wonder to unravel.
This entire deep dive has truly shifted my perspective. I'll never look at a sunrise or a night sky the same way again.
Right.
There's so much more going on than meets the eye.
I think that's a wonderful takeaway from our exploration today. We're all passengers on this extraordinary journey through space and time. It's a journey filled with awe-inspiring wonders, intricate movements, and a profound sense of interconnectedness.
So the next time someone asks me what I did today, I can honestly say, oh, just traveled millions of kilometers through space.
And while they might think you're joking, you and I will know the truth.
Yeah.
We've gained a deeper understanding of the incredible cosmic dance we're all a part of.
Yeah. Exactly. We're in on the cosmic secret now. Thanks for joining us on this incredible adventure. And until next time, keep looking up, keep exploring, and never lose that sense of wonder about our place in the universe.
And remember, you're moving much faster than you think.